So this is about some joint work in progress with Franziska Jahnke. And so here's a very short summary. So basically there's a certain foundational theorem in modern p-adic geometry, which is called the almost purity theorem. And this is a theorem which is, as the name suggests, only true in an almost sense. And basically the goal of this talk is to remove almost. So more precisely, we want to identify a class of Banach rings for which the above theorem becomes true on the nose, so with no almost. And then basically we want to recover the original statement using some kind of ultra products. So that's what we want to do. So first, let me recall what this almost purity theorem says. So this is a statement about perfectoid objects. So let me recall some definitions from perfectoid geometry. So a perfectoid field is a complete non-Archimedean field. So I'm using multiplicative notation throughout. It's going to be the most natural choice. Of residue characteristic P greater than 0, such that the value group is non-discrete, so things like the p-adic fields are excluded. And the final condition is the crucial condition. Namely, you have that the Frobenius is surjective modulo P on the valuation ring. So here K circ is just the valuation ring of K. There's a reason why I choose this notation instead of the more standard one. It will become clear later. So essentially this last condition allows you to extract pth roots of elements of your field up to some small error. Okay, so that's what it is. So the way you usually obtain such a field is you start with something that you encounter in usual life, like the p-adic numbers, and then you adjoin a compatible system of p power roots of p, let's say, and then you complete with respect to the p-adic norm. So this is a mixed characteristic example. A positive characteristic example is quite similar. So you start from the Laurent series over Fp, you pass to the perfection, and again, that's not quite complete. You need to complete it, and that's a positive characteristic example. So actually, the almost purity statement is a statement about perfectoid algebras, but first I want to state it for fields because it's maybe a bit more accessible. And essentially what it says is that if you take a finite extension of a perfectoid field, then it's almost unramified. Or actually it's better to think of it as almost defectless and almost unramified. So what does it say exactly? So yeah, I should say that this is often, of course, Tate did not formulate this. The perfectoid terminology was introduced much later, but in some sense he was the first one to observe this phenomenon in a special case. So what does this theorem say? You start with a perfectoid field and you take a finite extension. Then, first of all, L is itself a perfectoid field. And then the extension of valuation rings is almost finite etale, so there is almost no ramification. And this word almost here is meant in a technical sense, in the sense of almost mathematics, which was introduced by Faltings and developed systematically by Gaber and Ramero. And this is a slightly, or it's a bit technical, but actually the idea is extremely simple, and now I'm just going to explain what the main idea of almost mathematics is, and what this statement says, basically. So let's just look at a very simple example, just the example we had before, the p-adic completion of this classical field. And yeah, let's say that P is not 2. And let's adjoin a square root of P. So classically we would say that this is a totally ramified quadratic extension. But I will argue that in some sense it's very close to being unramified. So I will argue that this extension of valuation rings is very close to being finite etale. So in what sense is that true? So to see this, let's try to at least approximately describe this valuation ring of L in terms of the valuation ring of K. And one thing is entirely clear, namely that this L circ contains K circ, and it also contains the square root of P. Something which is less obvious is that it also contains a square root of a p to the nth root of P. And the reason for this is just this elementary calculation from high school, that if you take this fraction 1 over 2 times p to the n, you can write it as some integer over 2 plus some other integer over p to the n, which means that if you raise p to that power, essentially you can express it as a product of elements which lie in that field. So this p to the 1 over 2 times p to the n is actually an element of L, and it obviously has positive valuation. So this is inside there, and now you can increase n and get better and better approximations of what L circ is, but you're never going to get an equality on the nose. However, if n is large, then essentially the error is quite small, in the sense that if you look at the inclusion, let's say, as modules over K circ, then there's a co-kernel, but the co-kernel is actually killed by, say, a p to the nth root of p. And if n is large, then a p to the nth root of p has norm very close to 1. So it's not quite a unit, but it's very close to a unit. If it were a unit, then this co-kernel would be 0. So in that sense, the co-kernel is small. So since the co-kernel is small, then I can use this K circ, this finely generated K circ algebra, to actually understand the extension L circ over K circ. And in particular, since this is finely generated and flat, then I can say how unramified it is by using some kind of gadget like the discriminant. So the discriminant is going to tell me that, okay, the extension is not unramified, but it's given by this principal ideal whose norm is very close to 1. So just to summarize, the extension L circ over K circ is almost finite etale in the sense that it can be approximated by K circ algebras which are actually finite, and such that the discriminant which measures ramification gets closer and closer to 1 as you get better and better approximations. So that's essentially what an almost finite etale extension is in this, at least in this example, in this simple situation. Okay, so now we move to algebras. So essentially, perfectoid fields are the zero-dimensional objects in perfectoid geometry, and the higher dimensional ones are these perfectoid algebras. So in the definition of perfectoid algebra, so let's start with a perfectoid field. And then a perfectoid algebra is going to be a Banach algebra over K. So ignore this word uniform for a second. It's essentially going to be a Banach algebra, so it has a norm. The norm doesn't have to be multiplicative, it's only sub-multiplicative. And of course it extends the norm of K, that's what it means to be a Banach algebra. And now we have a similar condition to the one that we had before, namely that we can extract pth roots, at least approximately. So we have this sub-algebra, we have this subring A circ of A, which I will define in a second, and then we ask that Frobenius be a surjective map on this quotient, modulo P. So let me clarify some notation and terminology. So A circ, now it would be tempting to say that A circ is actually the unit ball, but there's a good reason not to say this, which I will explain in a second. Instead, A circ here is the set of power-bounded elements. So an element is power-bounded if the set of its powers is bounded. And if it happened to be the case that the norm is power multiplicative, that would be essentially the same as the unit ball. But I'm not assuming this. I'm only assuming that the norm is sub-multiplicative. So, but actually in the case of uniform Banach algebras, you do have a power multiplicative norm. So let me explain this. So a Banach algebra is uniform if one of the following two equivalent conditions hold. A circ as a set is bounded. That's one condition. And the second one is actually the one we're going to use, is that the norm, the given norm on the Banach algebra is equivalent in the sense that it induces the same topology to a power multiplicative norm, which is sometimes called the spectral norm of the Banach algebra. So actually, in the case we are interested in, there is a natural choice of a norm, which is this spectral norm. And with respect to that spectral norm, A circ is simply the unit ball. So feel free to ignore all the previous discussion and just think of, yeah?
Why did you say that A circ is bounded? Why is it not just...
So it's not automatic. Like, if you collect all these power-bounded elements, it's not automatic that this set, because the bound could get larger and larger for its, yeah. So that's why it's called uniform, actually, because you have a uniform bound.
And the second question.
Yeah.
So it's the norm is valued in K or is really valued?
So the norm is valued in the reals. Yeah. And I should say also that we're not assuming that the value group or the value group of K is equal to the value group of A or anything like that. But it's just the norm extends the norm on K. Okay? Now there is so the entire point of this perfectoid business is that essentially you have a way to associate objects of characteristic 0 to associated objects of characteristic P, and there's a very close connection between the two sides. So for instance, if you start from a perfectoid field of characteristic 0, then this tilts the perfectoid field of characteristic P. And then you have some nice theorems like the Fontaine-Vandenberg theorem, which says that the absolute Galois groups are isomorphic. And there is a similar construction for perfectoid algebra. So if you have a perfectoid algebra of characteristic 0, there is a way to associate a corresponding algebra of characteristic P. And again, you have a similar result, namely that the etale fundamental groups are isomorphic. Okay. So now I can state the almost purity theorem. So in the context of algebras, what it says essentially is that if you're in a situation where you have no ramification at the generic fiber, this implies that there is almost no ramification everywhere, which is a bit surprising. So let me state it a bit more precisely. So let A be a perfectoid algebra and A to B be a finite etale morphism. Then the following hold. First of all, B is a perfectoid algebra. And again, same thing as before. The morphism between the power-bounded elements, or between the unit balls if you prefer, is almost finite etale. So it's not going to be etale, but it's almost finite etale. So let me give you a picture. Let's say. So what does this theorem say geometrically? So let's use the language of schemes to understand this. So we have here the spectrum of B circ, which maps to the spectrum of A circ. So that's the morphism which is associated to the ring map from A circ to B circ. And the entire picture happens over the valuation ring of K, which can be thought of as a line. Yeah, actually, this picture is, of course, just a useful fiction. I mean, these objects are highly non-Noetherian, so you cannot even make sense of dimension and stuff like that. But let's pretend they are actually Noetherian. So what does this theorem say? So now you can look at this morphism over the so-called generic fiber. So this spec of K circ has 2 points. One is the generic point, which corresponds to spec K, and the closed point corresponds to the maximal ideal. And essentially the assumption that we have here is on the generic level, so we have spec of B here, which maps to spec of A. And we're assuming that there's no ramification here. So if you want, this is some generic information. And the conclusion in part 2 is about what happens in the special fiber. And in usual algebraic geometry, like if you have a morphism of varieties, for instance, and you assume that you have no ramification at the generic fiber, then essentially you know nothing about what happens in the special fiber. But somehow in these perfectoid situations, you get some information on this, on points of the special fiber as well. But you only get it up to this almost business. So that's the intuition. Any questions? I know that this might be a bit quick, but okay, I'll just continue. Okay, so what are the goals? Now I can state our goals a bit more precisely. So if you cross out the word almost in this statement, then it's just false. I mean, already the example that I presented before gives you a counterexample in the case of fields. So the goal is simply to discover or to identify a class of Banach rings for which this statement becomes true on the nose. So if you have a finite etale extension generically, then it's finite etale everywhere. It's finite etale integrally. And then the second part is to recover almost purity, the almost statement that I stated before, using ultra products. So it turns out that there is a connection between almost mathematics and usual mathematics via ultra products, which was essentially first discovered by Gabber. And then we essentially arrived at the same ideas a few years later, but with different motivations in mind. So I will first explain what I mean by an ultra product, because actually it's not what you think. So actually, since we are dealing with objects of analytic nature, like Banach algebras, it's much more natural to use the same kind of ultra products that are used in Banach spaces and in C-star algebras and things like that. So these are called Banach ultra products. And in continuous logic, there are many people studying these Banach ultra products. But as far as I know, the discussion so far has been restricted in the Archimedean context. And as I'm going to explain now, actually, there are very good reasons to initiate these techniques also in the non-Archimedean context. So, but the definition is actually exactly the same. So a Banach ring could be something, a C-star algebra in this definition. So basically you get, okay, let's start with some Banach rings. And we want to define their Banach ultra product. So the usual ultra product is obtained as a kind of quotient of the product, but here we want something which is equipped with a norm. So we don't consider the product, but rather the product in the category of Banach spaces. So in other words, this is the L infinity product. So you just get sequences which are bounded. So this is a normed ring with a supremum norm. And now we want to define Banach ultra product, so we start with an ultra filter. And the thing we are going to quotient out in this case is this ideal. It's sometimes called the null ideal of the Banach ultra product. So you just take the sequences whose norms tend to 0 in the sense of the ultra filter. So this is bigger than the thing you quotient out by in first order logic, in the usual ultra products. Okay? And the Banach ultra product of the AEIs is just this quotient. So some notation we will write, if you have a sequence of elements in the Banach rings AEI, we will use this notation for the equivalence class of the sequence. So this Banach ultra product is equipped with a norm, which is defined as follows. So you take a sequence, or you take a representative, let's say, and then the sequence of the norms lives in a bounded in a compact interval of the real line, just because we have taken the Banach product in the very beginning. And therefore, I can define the limit of this sequence along the ultrafilter. So I get a real number. So that's the norm. And now let me explain how to go from almost mathematics to usual mathematics. So again, the idea is that these Banach ultra products turn approximate behavior into exact behavior. So, and it's actually exactly the same reason, it's exactly this reason why these Banach ultra products have been considered in the Archimedean world, but in this context, the word almost has a slightly different meaning. But anyway, so let's go back to this example, and let's try to interpret what's going on there from a non-standard point of view. So recall that in the example we considered before, K was the p-adic completion of this field, and P was not 2. And L was this very simple-minded quadratic extension. And we made an observation before, namely that, there's a typo here. This should be just square root of p to the 1 over p to the n, not what's written here. So let me write it. So in the very beginning, L is given to us as a quadratic extension where you adjoin a square root of p, but you can actually express it also as a quadratic extension in this way for every n in the natural numbers. And now we can sort of take some limit of this p to the nth roots, because these ultra products, they have a very liberal notion of what a limit is. So essentially, every limit exists. So you consider the same situation in the ultra product, and you realize that actually you can now express the corresponding non-standard extension by adjoining a square root of a non-standard element pi, which is simply the, what's written here, namely the ultra limit of this p to the nth roots of p. And the key point is that this is actually an element which has norm 1 by construction. So since you're extracting a square root of a unit, essentially you get an unramified extension. So the corresponding extension of valuation rings is finite etale, not anymore almost finite or anything like that. So the almost finiteness that we had before essentially transformed into actual finiteness. Sorry, I meant the almost etaleness that we had before.
So the norm in the ultra product still goes into R?
No, it goes into R. So when you take the Banach ultra product, it is equipped with a norm, right? So if you think of maybe of the usual ultra product, that's like the rank 1 part of the standard decomposition. That's exactly the norm you get. Yeah, I should say that actually all this discussion was done originally in our paper with Franzi in the context of first order logic, but since we are dealing with Banach algebras today, it's actually more natural to present things in the continuous logic, and that's why I'm changing the game a bit. But it's essentially the same idea. So yeah, something that I should point out, and actually it's related to your question. So Banach ultra products or Banach ultra powers do not commute with taking power bounded elements. So if you take the ultra power of the valuation ring, then that's a valuation ring of higher rank. Whereas if you take the power bounded elements of the ultra power, then, well, it's always a rank 1 thing. So this is a localization of the left-hand side. You have to invert some elements which are which have sort of valuation infinitesimally close to 1. And yeah, the entire point is that ramification still persists at the level of these higher rank valuation rings, but essentially once you localize, so once you pass to the rank 1 norms, then this kills all the ramification. Okay? Now, let me discuss some facts about ultra products of perfectoid algebras. And the results I'm going to present should follow from an appropriate generalization of, well, there has been a recent preprint by Ridoki, Cucci, Scanlon, and Simon. And essentially, the results I'm about to present should follow from a suitable generalization of these results. So essentially, what they prove is I'm not going to state it precisely, but it's essentially a bi-interpretability result between K and K flat in the context of continuous logic. And it seems likely that this result generalizes in the context of algebras. And this is some ongoing work by van der Saf. So we start with the perfectoid. So essentially, this proposition says that tilting commutes with ultra products, but you have to consider Banach ultra products, not usual ultra products. Okay, so you start with a collection of perfectoid algebras. Sorry? Okay. Yeah, you start with a collection of perfectoid algebras, and then, first of all, when you take the ultra product, that's also a perfectoid algebra, you can also describe the power-bounded elements in a similar way in terms of the ultra limit or ultra product of the power-bounded elements for its AI. And a key observation, which will be used later, is that what I said before, tilting commutes with ultra products. So the tilt of the ultra product is the ultra product of the tilt. But it's crucial to use Banach ultra products for this to make sense. And something else which, I mean, I'm not going to use this later, but I thought I just might be interesting to mention, is that tilting preserves elementary equivalence even in the context of algebras. And that essentially follows immediately from the previous fact and the tilting equivalence. Because, for instance, if you know that A flat is elementarily, yeah, by the way, this elementary equivalence is meant, again, in some form of continuous logic, specifically unbounded continuous logic. But even if you don't know what it is, essentially, the structure of the proof is quite simple. So let's say you assume that the tilts are elementarily equivalent. Then by some kind of Kistler-Sella, essentially you can find isomorphic ultra powers. But now we also know that tilting commutes with ultra powers. And we also know that we have that the tilting induces an equivalence of categories between perfectoid K algebras and perfectoid K flat algebras. So essentially, you get that this is an isomorphism as well, and then you can go back. So it's really a formal consequence of these two facts. Sorry? Yeah. Okay. So now, let me say, so I gave an example before of how to translate almost mathematics to usual mathematics. Now I just want to make this a bit more systematic. So again, let's fix a non-principal ultrafilter for the rest of the hour. And let's say we have a morphism of non-Archimedean Banach algebras. Then, well, I gave an example before of this phenomenon. Essentially, almost finite etaleness is the same as asking for finite etaleness at the non-standard level. And using this, essentially, you can state a non-standard version of almost purity. So if you start with a non-principal ultra power, of perfectoid algebra, and you take something which is finite etale, so this happens generically, then this etaleness extends integrally. That's essentially a non-standard way to express almost purity. And again, the question is, well, what algebraic properties does this ultra power have which allow such a statement to be true? So, in the case of fields, essentially the answer turned out to be extremely simple. So, if you start with a perfectoid field K, and you take a Banach ultra power, then this is just a tame normed field with a divisible value group. And from this, it's very easy to deduce almost purity. So I briefly want to recall this story because otherwise the generalization to algebras will not make sense. So I will briefly recall what we did in some previous work with Franzi. But first I want to recall some definitions related to tame fields, which were also discussed in Kettles and Stock. So recall that a finite extension of Henselian normed fields is tame if the associated extension of residue fields is separable. P does not divide the ramification degree, the extension of the degree of extension between the value groups. And the crucial condition here is that the extension is defectless. So in other words, the degree of the field extension is equal to the product of the ramification degree and the inertia degree. So usually what you have is some kind of multiplicative error in this equality, which is a power of the residue characteristic. And not having such an error is essentially what defectless is about. And we say that, yeah, by the way, did I say, yeah, this was introduced by Kuhlmann. And a Henselian normed field is called tame if every finite extension is tame. Okay? Now, actually, there are some alternative characterizations of tame fields, which are again from the same article. So, K is tame if and only if K is defectless, the value group is P divisible and little k is perfect. If and only if K is algebraically maximal, so this means no finite immediate extensions. And again, the value group is P divisible and the residue field is perfect. So you can actually also replace algebraically maximal with another condition, and that's actually a key point, so let me emphasize this. So recall that actually algebraically maximal is equivalent to being algebraically pseudo-complete. So this is a condition in terms of pseudo-Cauchy sequences. So a pseudo-Cauchy sequence is a sequence for which the distances between the terms get smaller, at least eventually, but they do not need to converge to zero. So it's just like a Cauchy sequence, but this is just decreasing. We do not require that this goes to zero. And a field is pseudo-complete if every pseudo-Cauchy sequence has a pseudo-limit, which can be thought of as in terms of decreasing sequences of balls. So this also says that, well, it equivalently says that every decreasing chain of balls has a point in the intersection. It is sometimes called spherically complete. Okay, so this word algebraically here means that you do not consider all pseudo-Cauchy sequences, you do not consider all such balls, but only those for which the centers satisfy some algebraic condition. It's not really that important, so you can think of spherical completeness if you prefer for the entire talk. Now, actually, the equivalence between all these conditions of tameness is very crucial, and it's actually going to be the key point when we move to algebras. So try to keep that in mind. But now let me finish the proof of almost purity in the case of fields using these non-standard methods. So far we have perfectoid fields and we have tame fields. And now I'm saying that you can tame perfectoid fields. So in the following sense, so if you take a perfectoid field and you take a Banach ultra power, then this is going to be a tame norm field with divisible value group. And there's also a converse, namely if you start with something, complete normed field, such that the Banach ultra power is tame, then the original field has to be perfectoid. And well, the key point, which is actually not at all hard to prove, is that when you pass to these Banach ultra powers, essentially you get spherical completeness for free. I mean, almost by design, essentially. Like if you have a pseudo-Cauchy sequence of standard elements, let's say in K, then essentially the pseudo-limit is just given by the corresponding sequence in the ultra power. So, okay, so we know this. Now let's prove almost purity in the case of fields. So recall what we have to prove. We take a perfectoid field and we take a finite extension. We have to prove that this finite extension is perfectoid and that there's almost no ramification. Okay, let's start with 1. So first, observe that that's a classical fact. Finite extension of tame fields are tame. So using the original definition that I gave, it's pretty clear. So you check that finite extensions of defectless fields are defectless. Finite extensions of perfect fields are perfect, and so on. It's not hard to prove. And now let's see how we can prove part 1. So we start with K, which is perfectoid. Then we know by the proposition that its Banach ultra power is tame. But that means that the Banach ultra power of L is tame as well, because of this observation. And again, by the same proposition, we can go back and deduce that L is perfectoid. Okay? So let's try to show part 2. So since this Banach ultra power is a tame normed field with divisible value group, essentially all ramification is trivial. So this is unramified, which is equivalent to saying that the extension of valuation rings is etale, finite etale. But you also have this dictionary between almost mathematics and real mathematics, which tells you that this is almost finite etale. Okay, so this follows quite easily from what we have discussed so far.
Going back to the proposition, for perfectoid, it's enough that the value is
Oh.
divisible, I understand. How does it become divisible in the ultra prime?
So you take the norm, so actually the value group isn't the reals, right? Because you take, yeah. So, yeah, maybe I should emphasize this more. We always equip this ultra power with the norm, with the rank 1 bit. Of course, the value group of the microbial value of the higher rank valuation that you have is not going to be divisible. Yeah, that's true. Okay. So now, essentially, we want to do exactly the same thing for rings. Okay? But it's actually a bit complicated. And one of the reasons it is complicated is because, well, one difficulty is that you want to mimic the definition of a tame field in the case of algebras, and there's a clear object that should be the replacement of the residue field, namely a circ modulo the maximal ideal from the maximal ideal of the field. So this would be the analog of the residue field. But there is no good analog for the value group, actually. So you could try to consider something like the multiplicative group of A modulo the multiplicative group of the power bounded elements, but for technical reasons, which I will not explain, it's not quite right. So for this reason, it's actually a bit better to use a construction by Temkin, which has a very similar flavor to the RV construction, which is probably more familiar to this audience. And this construction essentially combines the value group and the residue field in one structure. But compared to the RV structure, this has the advantage that it's actually a ring. It's actually a ring, not... and I'm going to use this construction quite heavily. So let's start with a non-Archimedean normed ring. And okay, for its real number gamma, let's say that this is the closed ball of radius gamma, and this is the open ball of radius gamma. Now the graded reduction ring associated to A is this graded ring right here. So simple to describe. And the construction is completely functorial. So if you have some bounded homomorphism between Banach algebras, then it induces a corresponding morphism, graded morphism of graded rings. So, and if K is a normed field, then this graded construction is sometimes called a graded field. So it means that every homogeneous element of degree 0 is invertible, and it's called the graded residue field of K. It should be noted that the graded field is not a field, which is a bit confusing. For instance, if you take the p-adic numbers, then the graded residue field is something like this, Laurent polynomials over Fp. And now, using this object, essentially you can reinterpret what tame ramification means. And for instance, there's a small paper by Antoine Ducrot, where he shows that essentially tame ramification is the same thing as, is the same thing as saying that the extension L over K comes from a graded residue field extension of K of the same degree. So in some sense, puts tame extensions on the same footing as unramified extensions or unramified defectless extensions. So this language is extremely convenient, actually. It takes some time to get used to it, but it's quite useful. Okay, so we know this. Now we want to define Tame Banach rings. And again, there are going to be several definitions. One in terms of ramification theory, which is going to be analogous to the original definition of a tame field, and one in terms of pseudo-Cauchy sequences. And then the entire game is to actually compare these two. So, but this is in some sense the correct definition. So let A to B be a finite etale extension of uniform Banach algebras. Basically, we want to say when this is tame. So it's going to be tame simply if it induces a finite etale extension at the level of graded residue rings or graded reductions, and the ranks of the. So here this notation means the rank of B as a finite. So B is a finite projective module over A, and this notation just means the rank of this finite projective module. And similarly for the graded reductions, right? So we ask that the graded homomorphism is finite etale and has the same degree. Okay. We also say that A to B is strongly tame, so that's going to be the analog of an unramified extension in the context of valued fields, which comes an extension which comes from an extension of the residue fields of the same degree. So we say that A to B is strongly tame if the corresponding morphism between the power bounded elements is finite etale and the degrees agree. Okay. And we say that a uniform Banach algebra is etale tame, or respectively strongly etale tame, if every finite etale extension has this property. So this gives you back the notion of tameness in the case of fields. So actually, if you look at it, so it gives you back the notion of separable tameness, but since everything is complete here, it doesn't really matter. So yeah, this generalizes the notion of a tame field, at least in the normed case, rank 1 case. And now we can essentially restate what almost purity says in slightly different words. So if A is perfectoid, then almost purity, what it says is that if A is perfectoid, then the Banach ultra power is strongly etale tame. So this class, I mean, you can immediately verify some properties about this class of etale tame algebras, which are analogous to what you prove for tame fields. So for instance, if you have an etale tame algebra and you take a finite etale extension, then this finite etale extension is also etale tame. So this class is closed under finite etale extensions. And so this is the analog of the fact that if you take a finite extension of a tame field, it's tame. And the proof is quite simple. So, I mean, let's do it. So essentially you have so you assume that this is etale tame and you want to show the same for B. So you just take a finite etale extension of B and you have to show that this is etale tame. But now just consider the corresponding extension between the graded residue rings and observe that essentially by assumption you have that this is finite etale and this is finite etale. And then there's a so-called cancellation law for etaleness, which allows you to deduce that this has to be finite etale as well. And then the multiplicativity of ranks for projective modules is going to give you well, the condition up there. So conceptually, it's very similar to how you prove well, the same statement for tame fields. There is also a related notion which was defined a few years ago by Katharina Hubner in an article which is called The Adic Tame Side. So the notion she defines is actually very closely related to what I defined here, but it's in a way it's a local notion, whereas what I defined here is a global notion. So you can associate to this Banach algebras some spaces called Adic spaces. And then you can define what it means to be, let's say, tame or strongly tame in the local sense. Yeah, so the definition I gave here essentially implies Hubner's definition, but the converse probably requires some acyclicity statement to go from local to global. So, okay. So this is one definition of tameness. Now I want to give a second definition in terms of pseudo-Cauchy sequences. And the second definition is going to be the one which is going to be easily verified for ultra powers, essentially. So first, let's observe something. Let's observe that if you have a normed field, then saying that the residue field is perfect and the value group is p-divisible can actually package it into one condition, namely that the graded reduction is a perfect ring. So that's a simple exercise. Or you can also say that RV is p-divisible if you're more familiar with this language. So that's a simple exercise. So in particular, we can. So in particular, a tame field is precisely an algebraically pseudo-complete field for which this graded residue ring is graded residue field is perfect. So now we're just going to say the same words for algebra. So we start with a complete tame normed field, then a PC tame algebra. So PC stands for pseudo-Cauchy or pseudo-complete, as you prefer. Is just going to be a uniform Banach algebra such that A is algebraically pseudo-complete. Again, feel free to think of spherically complete with respect to the spectral norm. And the graded residue ring is perfect. So equivalently, if you don't want to think about graded rings, this has the same content as saying that for every element A, you can find another element such that you cancel the leading term, so to speak. So the difference between A and B to the P is less than the... the norm of the difference between A and B to the P is less than the norm of A. So now we can immediately tame perfectoid algebras in the exact same way. So if you have a perfectoid algebra and you take a Banach ultra power, then it becomes tame in this sense. I mean, essentially the proof is exactly the same. You get spherical completeness for free. And and the second condition is also automatic. So now the key question is, how do these notions relate? And in particular, is it true that if you have something which is tame in the pseudo-Cauchy sense, then it's etale tame? Because if we have such a statement, then we are very close to proving almost purity. And today, essentially, I'm just going to present you a result in this direction for Galois P extensions. So this statement is true if you only restrict your attention to Galois P extensions. So let's formulate this precisely. So you start with a tame or PC tame algebra, and you take a Galois extension where G is a finite P group. Then two things happen. So B is also tame, pseudo-Cauchy tame, and the corresponding map at the integral level is G Galois. So you started with something which was only finite etale generically, and then your conclusion is that the same thing happens at the integral level. So it's a strong purity statement, but it's only for this P extensions. So in other words, using our previous terminology, this map is strongly etale tame. So from this statement, you can immediately deduce the almost purity theorem for P extension using Banach ultra products and the dictionary between almost mathematics and mathematics. So some comments. First of all, if you only assume A to B to be just a finite etale extension, then there's no reason to expect that the corresponding map at the integral level is finite etale, because this already fails for fields. But it might be true that this statement is also holds in the P power degree case, which is not Galois. So for some reason in the proof, it's needed that A to B is a Galois extension. And I will now explain some elements in the proof. Really? Okay. Okay, so let me explain some ideas. So this is the statement again. You start with a PC tame algebra and you take a G Galois extension. Then we want to show that B is also PC tame and that the map at the integral level is etale in particular, G Galois. Okay. So first of all, we can immediately reduce the case of Z mod P extensions because, I'm only going to give the proof in characteristic P because there are some subtleties in characteristic 0 which I don't want to discuss. So you reduce the case of G equals Z mod P because in the general case, this map from A to B is just a tower of Z mod P extensions by group theory essentially and Galois theory in the context of rings, and then you just induct on the tower. So we are reduced to this case, and now Galois theory actually works, or Artin-Schreier theory works exactly the same way for rings. So B is given by an Artin-Schreier equation where A is some element in A, and we can actually assume that the norm is greater than 1. So the norm here is always going to be the spectral norm, And that's actually going to be important. So if the norm is less than or equal to 1, then this equation is already etale at the integral level. So there's nothing to prove, essentially. The two conditions are quite easy to verify. So let's assume this. And now let's try to do something which is quite common in the case of fields. So we build a pseudo-Cauchy sequence of this form. So an is going to be a to the 1 over p plus blah, 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 a to the 1 over p to the n. And note that this is a pseudo-Cauchy sequence because if you take a successive difference, so this is a key point. If you take successive difference, you get essentially only the final term because you have some telescopic cancellation going on. But the norm of a to the 1 over p to the n plus 1 is also the norm, is also the p to the n plus 1 root of the norm of a, because the norm is power multiplicative. So here we crucially use the fact that the spectral norm is power multiplicative. So in any case, you get a pseudo-Cauchy sequence. So then you also have a pseudo-limit. And once you have a pseudo-limit, essentially you do exactly the same thing you do in the case of fields. You make a change of variables, essentially, to get some equation which is visibly etale over a circ. And then the rest is easy. You can check that B circ is Galois over A circ. And there's some extra work into showing that B is tame, which has to do with valuation basis. But, so that's more or less the proof. And in characteristic 0, somehow, for some reason, you have to use something which is not at all trivial, which is that the Picard group of A is p-torsion free, and that allows you essentially to get a global equation. So there are some local to global issues in characteristic 0 that you have to deal with, which are essentially addressed by this result of Batt and Solzen. So let me stop here. Thanks.